So my name is Heather Miller. I'm a Ph.D. student at EPFL. I work with Martin Odersky on Scala a lot of the time. Actually, all of my life. That's all I do. I mean, I might have been responsible for annoying documentation. So if you're annoyed by documentation, it's probably my fault. If you're annoyed by lots of different things, I could be involved in you being annoyed. Sorry in advance. Since I got involved in all the Scala stuff, I've been working on lots of different things. I was involved in the Futures and Promises library, all the documentation, and lately I've been working on trying to make Scala a little bit nicer to use when you're moving data around, basically, or when you're operating on a bunch of data. That's sort of the thesis statement of all the things that I try to do. But I try to do it from the language of the level. I'm sorry, the level of the language. And so today, I've given this talk once or twice before. It's about a research project that I'm currently working on. It's not, it's just a bunch of cool ideas. Something that we built and we're playing with it, and we've implemented a bunch of things using it, and it seems to be pretty interesting and useful. It seems to have its own specific sort of niche use cases. But this is actually a project that's currently underway in the middle of the design phase. So details are changing, so what you see could change in a month or something like this. But this actually, it works. This actually brings together two projects that I've recently worked on that you might have heard of before. One is this serialization project called Scala Pickling. And the other is this thing called spores, which I'll talk about in a second. But the serialization project is actually, it's actually kind of an interesting project because the idea is that you do serialization totally differently than usually you do, in the JVM. You try to do as much of it at compile time as possible. Then you inline sort of the formats and whatnot that you actually want to use at the use site where you are actually trying to serialize data. You serialize it at compile time if you can. You can't always serialize at compile time, but we try to do it that way the most. And so it's really performant, and then it's also really flexible because you can change formats and stuff. It's a pretty cool framework. And it's also all based on type classes. So if you know what type classes are, that's great. If you don't, doesn't really matter. The nice thing about type classes is that you can compose them and do cool things with them, make them do all kinds of stuff in your programs, and they're kind of a powerful tool if you know how to use them correctly. This is actually, one cool thing about this framework is that it's built using these type classes, but at compile time. So the actual, when the code is compiling, the compiler is composing type classes. And that makes it possible for you to add your own serializers that you write yourself that are pretty small if you want to just escape from Java serialization and then patch how Java does it. Well, how this framework does it, not Java necessarily. But also, this is how you input your own serialization format. And then the other thing is spores. They're a funny name. They are a closure-like abstraction that are safe and guaranteed to be serializable and don't grab crazy object graphs. And so the idea is that you should be able to send these things over the wire and use them in situations where you want to move some function to some data somewhere. That's the goal of this. So, and also there's research that we've done in this direction. There's research that we've done in the direction of adding type constraints, so you can actually control the environment and all kinds of things that these closures capture. So people can't capture actors or sockets or things like this. That's more like research, but the portable sort of serialization, serializable closures thing is actually not super researchy. So these two things exist, and this talk actually kind of brings these two things together in some way. So it builds on the basis of these serializable functions to provide some sort of substrate that if you were to build a system yourself, if you're going to build Spark, for example, or something else where you're making two different machines communicate, or you've got two data stores you're coordinating between. The idea is that you want to, maybe bring these two things together well, actually, the idea is to bring these two things together in a nice programming model that is based on this idea of oh, am I ahead of myself? Okay, yeah, I can usually I can see what I'm talking about. Okay, so Yeah, so the idea is that you have this nice stateless programming model that like makes it a little bit easier to recover from failures or handle failures yourself, and also to maybe keep stuff in memory, and also do a little bit of debugging on the sort of like the debugging communication and the level of like distribution between machines, because if you actually like hack around in a bunch of like frameworks that do communication between machines, you find that like a lot of type information goes away, and then you kind of get like lost with what you tried to send over the wire or what something is that you receive on the other end. So debugging and types like at that level are pretty useful. And the whole point is that this whole thing is actually very like clean and functional. It's totally stateless, and it's all based on like these immutable sort of data structures that I'm going to show you in a minute. And again, it's a research project. We're working on a paper right now. Details are changing of the design, so don't like, etch this in stone or anything. And Databricks let me do this for, probably 20% of my time there, so that was really nice of them. So I have to say thank you to Databricks for letting me spend time on this. But the fundamental idea is to actually kind of invert the actor model. So if I'll show you what I mean in a moment, but this model is kind of like a dual to actors if you look at it that way. And it actually can work nicely with actors if you play with it a little bit. So you might, okay, all right, what does that mean? Whoops. If you look at actors are, you can think of them as something that exists on one machine that typically kind of protects some sort of state that, and makes it easier to reason about things happening concurrently, like these agents kind of, or actors rather, talking to each other. There's a message handler that the actor has that represents sort of all the stuff that you're supposed to be doing to that state, right? And you're sending data between these actors. And the whole idea is that when you receive a certain message, then you do some action based that's sort of implemented in this event handler, or sorry, this message handler. And if you look at it, like, and you squint your eyes, what you're doing with an actor is you're exchanging data or commands, whatever you want to call them, through asynchronous messaging, right? That's sort of the like, if you zoom out and look at it. This function passing stuff is basically the opposite. So rather than keeping your functionality stationary on one machine, we keep your data stationary on one machine. We don't let you mutate it, and then we let you pass these functions around to actually to do a bunch of transformations on your data. So think about it kind of like how we work with lists or things like this. We chain a bunch of transformations to something, and we have a bunch of sort of like functions that we apply to that we pass to high order functions, and you wind up with this like sort of transformation on an original piece of data. So that's the idea. Like that's the basic idea. And so I also would like, so people always say, oh, well, this is something where you're passing these functions around. This is actually not a new model of like concurrent processes. It's just like a new means of working with distributed data in like an inverted way. So don't think that there's going to be some interesting calculus or something about this. This is not up that alley. Actually, I was going to make a point about this. This is actually. There's this cool paper that was written in 1994. It's actually like an essay. It's not a paper. It's like a discussion. And it lists a whole bunch of things that we don't really do nowadays, even 10 years later, when we build systems. There's a bunch of sort of design constraints, or rather design decisions that people who build systems like don't always follow, or frameworks for doing things in some distributed way. And like the one kind of quote that I like from this paper, it identifies like four things: latency, memory access, partial failure, and concurrency. And not like making this part of your it basically alleges that if you don't make this part of your computational model or the programming model that the programmer uses, it's a bad idea. And I mean, there's a lot of reasons why. You can read the paper. But what they suggest is that, well, a better idea is to accept that these things exist. Don't pretend like they don't exist. Don't try to abstract over them and say they're not there. Don't say that latency doesn't exist. Don't say, so I can just read the quote, a better approach is to accept that there are irreconcilable differences between local and distributed computation. Don't pretend that something that is simple to reason about on one machine should be like exactly transparent and the same on all other machines, right? Instead, be conscious of those differences, all these four things, at all stages of the design and the implementation of distributed applications, and rather than trying to merge these two objects, local and remote, engineers should be constantly reminded of the differences between the two, know when it is appropriate to use each kind of object, and be sort of exposed to these things like latency and whatnot, like know they exist. I bring this up because these things are kind of also, like, if you look at the actor model, I mean, these things are kind of exposed and visible. If you're trying to use actors, you have some notion of latency, you have some notion of concurrency. All of these things are not hidden from you. And we try to do the same in this model where we're sending these functions around. So that's a bit of an introduction. I made a bunch of little illustrations to show what it looks like, so you can kind of get some intuition about it. So the first thing, there are two concepts. So like I said, your data is stationary, it stays on one machine, and it's immutable. And you have these functions that you can move around. So you can apply these functions to data on different machines. I have a really stupid name because I started with the tradition of naming things stupidly after spores. I have to name it silos right now. If somebody wants to suggest something better, please let me know if you're better at naming. I do computer science, so I'm bad at naming. And the other thing is, are these spores things. So the silo, the idea of this silo is something that holds this immutable data. OK, so what are they? First, I'm going to show a picture of how you use them. So there are two things, actually. A silo exists kind of like an actor. Are people familiar with actor systems? Do you use actors ever? Like, can I see a raise of hands? Like, okay, show of hands? OK, so an actor ref, you guys know what that is? OK, cool. All right, so you use these things to basically, on one machine, to talk to a remote actor. And that's the idea. So we have the same kind of idea. It's just that they're called, for a lack of a better name, of course, silo ref. And forget about master, worker, it doesn't matter. These are just two different machines. On one machine, you might have a silo ref, which is the thing on the right, sorry. And on the other machine, you would have this big, chunky, blocky thing. It would be like the actual data container, the thing that holds the data, the thing we call a silo. And the idea is that you build kind of a data structure by operating on the silo ref. So if I start applying functions to this thing that represents a piece of data, just think of it like an option or something else. You apply you get something out of it, you apply some function to it, you get another option or something out. You can kind of like make a tree of things that you've done to this original piece of data, like by applying functions to it in different ways. So it kind of like oops, no, it's gonna do the whole animation now. OK, well now you saw the animation. All right, so the idea is that you use this representation of this data that you have distributed elsewhere. It doesn't all have to be on one machine, actually. These silo things can also exist on other machines. These silo refs just point to where they actually live. And you do all of your operations on these little silo ref things. So you're basically applying functions to your pieces of data. And that's how you use it on one machine. And basically what happens is you wind up, so these little dotted lines like represent the sort of like the reference to this distributed, or this object on another machine. And the arrows, the solid arrows, are basically kind of like a tree of transformations that you might do to it. So like, let's just imagine that this is a list of something, like a silo of type list of something. Sorry. Like maybe this is some map, I don't know, another map or a filter or reduce or something. Like you have like a tree of transformations or operations that you do on this piece of data. That's like the basic sort of picture. And again, I highlight like that, you can have this guy like on some other machine, and don't worry, it all kind of still makes some kind of sense. It's just that you know that you're dealing with a silo ref, and you actually never touch the actual silo. And that's the basic idea of the silo thing. You have a few primitives as well. 3 right now. I'm trying to make sure this stays as small as possible. OK, so again, silo ref points to the silo. So you might have a silo ref of some type T. These all have type parameters. So silo ref of type T points to a silo of type T, right? And you look at the silo ref thing as the workhorse, the thing that you do all of the work on to like get some job done, right? There's this method apply, send, and another stupidly named thing, looking for better names, called pump2. So there's this apply method is actually lazy, and I'll show you what that means in a minute. Why? Basically, the idea is that you can build richer logic by composing functions together that do sort of complicated things. But maybe you don't always want to like kick off that computation right away. So I mean, you can. I guess one way to think about it is if you use Spark, you don't. You're not like eagerly doing like every map or anything like this. Like only when you maybe like actually need to kick off that computation will you actually do it. It's the same kind of idea. You don't have to like this is lazy. It figures out how to apply functions together. It like kind of queues them up, and then there's another. Whoops. Oh no. So basically, it queues them up. and it defers the actual application of these things to your remote data until you force it to be sent, until you send it over the network. And that's the send operator. That's actually eager. Whoops. Oh, yeah. So the send thing, with apply, you apply a spore. In this case, there are two. We're working on figuring out whether or not 2 or 1 are necessary. It doesn't matter so much the details why now. I can talk to you more if you want to know why later. But it returns the silo ref that represents the new piece of distributed or remote data that will one day eventually be materialized. So you can keep on operating on it. It doesn't actually have to be materialized yet. It can be materialized later, but you can chain all kinds of operations to it. And then only when you push, when you push sort of the send button, when you force this, do these functions get sent over the wire? Do they get applied? And then eventually, this silo ref that points to your piece of data, it all connects and completes. And I'll show you in a second. Again, another illustration to maybe make it a little bit more clear. And the send operation actually just does the real send, and you get back a future representing the result type that you want to get back from your distributed data or your data on another machine. So this is all asynchronous. Whenever that work gets done, eventually you'll receive it back in the form of a future, and it'll be completed. And sometimes you need to move data. So if you think about some kind of distributed group by or something like this, you need to move data around to do these things. So that's what this thing is about. This pump 2 thing. It's a way of actually shuffling or moving data, basically. So you need some way to do that. Could you push the thing? Yeah, thank you. So sometimes you need to do that. And basically the idea is that it defines how you should, so there's this spore, this function, that should define how to transform each piece of data and then where to send it to, basically. So this is important. It needs to exist if you ever want to actually do any sort of real building of a system. I'm going to show you another illustration again. So maybe I can fill in what the silo ref and what these messages kind of look like now if you send a function. So let's just say you have some silo of type T and a silo ref which points to that silo of type T. That silo ref is also of type T. And let's just say you want to do something to your data. Like I said, maybe whatever you want to do represents a map. Maybe there's a list inside of your silo, and you want to do a map on all the things inside of it. Doesn't matter. What you do is you can use this apply function plus the send function, basically, to you define your function, how it should be applied to the data inside, and you just kind of do your send, and you get back this new silo ref. So this is kind of like a list, right? But it's all lazy, or rather, it's all asynchronous, and it happens between machines, basically. So if you have if you pretend this is a list, you have a list of T, you do a map on it, you get a new list out of T. Same idea, right? You're kind of doing these transformations on collections, if you're familiar with these kind of things. Okay. When this function gets to this machine, it gets applied by the runtime. So there's something that receives the messages and applies them to the data that they point to and all that. That's part of sort of the runtime that's running. Eventually, a new piece of data, silo of type S, appears, and this silo ref that points to it, can actually start getting new messages to that piece of data. So you can actually be using this silo ref of S before the silo of type S is materialized. The runtime queues the messages and then sends them whenever the silo of S is actually materialized. Is that clear? I mean, if it's not, I am happy to explain things 20 times. It's totally fine.
Where is the send? When does the send happen?
So I just pretended I did apply and then send. So let's just say apply this function dot send now, and then that's kind of the illustration.
And where is the value that is returned by the future?
So this is just applying and actually good question. I didn't illustrate that back. There's another example where you'll see that. Don't worry. Okay. Oops. Oh, and another point again. This all doesn't have to be in this this machine and that machine mode. You can mix these things. You can have silo refs on some machines with silos on that machine that have no relationship to one another, and you can mix them in any way you want. Just like you can put actors in any way on any machine and have actors with other references on other machines. Oh, yeah, there. See? Okay, so I will get back to your question when I talk a little bit about what these spore things are, and then I'll answer by trying to do like again, I can't show all of the details, but I will show you how to do kind of like a little map reduce kind of thing on these things, and you'll see the result coming back. So now these spore things. Does anybody are you familiar with these? I want to know how much I should ramble on about them. Does anybody know about these things? Okay, cool. So I can actually give you a bit more detail. So these things, I like to keep using this definition. They are small units of possibly mobile functional behavior. They are not actually, they subclass functions, but they are not functions themselves. They have extra, they are functions, they contain a function, but they are a separate abstraction because you need extra checking, you need some extra work done to make sure that you don't get a crazy object graph and all kinds of other stuff happening when you're trying to send these things around. Also, if you want to go into gory details, I recommend you look at this. It's a Scala improvement proposal. It talks about all the stuff that is valid to be inside of a spore thing and what's not. It's at the bottom of the screen, but I'll tell you now in case you want to write it down. Anyway, so yes, they're closure-like abstraction for use in distributed or concurrent environments. I can explain how they're useful in concurrent environments. Right now we're talking about sending things over the wire, so I'll focus on that. But really, when we built these, or we came up with this idea, the idea was to have well-behaved closures with controlled environments that can avoid all kinds of hazards that end up happening. And there are numerous really inelegant, stupid, ugly hazards. And these include memory leaks, so accidentally capturing something you didn't know you captured in a closure and keeping it around forever. Race conditions due to capturing mutable references. So if you capture a var of something and some other thread can just keep on mutating it and you think it means something, it changes over time, right? That's not good. That happens actually. And what I care about a lot lately is these runtime serialization errors that occur to unintended capture of references. So that means you accidentally captured perhaps maybe your enclosing object or something like this, but you can't really tell from looking at the code. It's just because we translate these things into objects and there's some sort of ownership chain, or rather a chain of things that are outer to it, and accidentally things can get pulled in basically that you don't know actually. If you had any idea what any of your object graphs looks like, you guys would all be disgusted because they're so confusing. Anyway, so this is the longhand form. This is what they look like, and this is when they're ugly. They can be shorter and prettier, but this is everything that they look like, completely all of them right now. So you have this thing called, I call it the spore header. There's two parts. There's this thing, right? This thing called helper right now, and then there's the actual function. Okay, so those are the two parts. This represents the environment, and this is the actual function that you want to send around. So the basic idea is that this code will not compile if anything inside of here references anything outside of the spore block. What that means is that you have to explicitly say what your environment is, basically. So that means you can't build a crazy object graph. There's more to it. You can have for comprehension, all kinds of other things. This gets more to be a little bit more detailed, but that's the basic idea. These things can also be implicitly converted. So if you have let's just say, well, I'll show you in a second actually. So there's also so basically everything so the rules or the guarantees are that everything that you capture has to be declared in this header thing. And the way that this all works is that the initializers of the things that are captured are executed once when you create the spore, when you create the local value thing, okay? So that means that what you actually put in there can't change over time. They're all vals and everything. So it can't change meaning. It can't be later initialized or as your program is running and something else in your program changes meaning. When you create it and use it, it's kind of fixed, basically. And then references to captured variables do not change, like I said. Also, very important to note, I'm not changing how things get evaluated here. There's nothing special. I'm not changing the rules of how stuff gets evaluated at all. If you remove this thing here, if you remove this guy, this is just a block, and it behaves exactly the same. So if you know what a block looks like in Scala, you make some curly braces, and you put some stuff inside of it, and that just is just a block of something that gets executed, right? This is the same. Yep. And also, they're related in that, well, one is a subclass of the other, but you can also implicitly convert functions to spores. So if you have an API, like some method that expects a spore, and some user has written a function, then it can be basically converted and then checked. And then you get a helpful error message that says, you captured something horrible. You shouldn't do that. So it's like very simple and kind of ugly maybe, but it can be made prettier. It's actually does a lot for you. It makes it sort of drastically changes the kind of stuff that you can be passing around in some sort of system if you're passing functions around, right? It really makes everything that you're sending over the network sane all of a sudden. So since captured expressions are evaluated upon spore creation, you can think of this all as you have a function with an immutable environment going around everywhere. That environment has nothing to do with one machine. You kind of make a local copy of that environment and you're sending that environment too. And also the environment is specified and checked, and there's no accidental capturing. You have to write your own environment so you don't accidentally capture Wikipedia. If you think about this, a cute little example here is maybe if this wasn't a spore and this was just a function, you could do Wikipedia.length or something, and maybe you accidentally capture all of Wikipedia and then try to send that over the wire. But I only wanted an integer. But you capture Wikipedia. I mean, these are kind of things where you have to explicitly say, put Wikipedia in my function, and you know what you're doing. Yeah, and you don't want to do that, right? That's common sense. OK, so I even drew a picture because I like pictures. So if you create one of these things and you create a spore, you put them next to each other, like I said, all the initializers, everything that you end up sort of, referencing, that all gets called right when the thing is created. So if there is so some objects or whatever, this is all specified in the environment and it's sort of solid in there. Whereas closures, you can have all kinds of vars in them. Something that you're calling could be unstable. It could be just a method that changes over time, whatever. This, you have no idea what it is from the time that the program starts to the time that it ends, basically. And it can change. It can grab all kinds of other objects over time. At one moment in time, it can point to something. Another moment in time, it can have point to 20 other things. You don't know. And spores always just kind of stay the same, and that's what's useful about them. Is it working? Yes. Oh, yeah. In your stuff, drag on your object graph. OK. So to reiterate, sort of the benefits of these things are that the captured variables are declared explicitly fixed, and that you can actually also statically ensure that everything inside of it that you've captured is serializable. So I can also this is another detail. You can actually, you can require that they're pickable, basically, that the serialization framework knows how to serialize them. So then you get statically, static errors saying, hey, that was a bad idea to serialize that thing because I can't serialize it. There's a research paper about this that we published this year, and it goes a lot more into other details other than just this shape and making sure that object graphs don't get crazy and whatever. This actually goes into, there's even a way to enforce that certain logical properties hold true of the stuff that you capture inside. So there's all kinds of again, you don't want to capture an actor, or maybe you don't want to capture a socket, or if you want to, well, not you, but let's just say you have let's just say you're Spark. Let's say you have an API that you give to users. You say, OK, pass a function to this thing, and we're going to send this thing over the network. A user can pass anything into it. But maybe you want to say, OK, well, don't capture the Spark context, or don't capture sockets, or don't capture something like this. So this is actually a way to prevent all of that stuff from being captured using the type system. And you can compose these things together. You can compose these functions together, and they keep their type constraints. So if you make some rule about what should not be captured, and then somebody composes that with some other function from somewhere else, that constraint holds and stays. So actually, that's kind of an interesting thing. But that's well beyond the realm of everybody in this room. Probably you don't want to do that necessarily. OK, so I told you I was going to give you an example now again, and it's going to be another one of these visual ones. So the idea here. You're going to have to use your imagination because I can't put everything on one slide. I want you to just get the intuition. Let's just say that you want to invent your own distributed list thing, and you want to have something that represents a map and a reduce operation. You want to just apply something to every element inside of your list, and then you want to like somehow combine all the elements in your list. And you want to implement these two pieces of logic, okay? And you have, let's just let's get down to the actual user code. You have a silo of listed int. Like, let's just see how this works. Imagine for now that you have this map and this reduced thing implemented in terms of these primitives that I gave you. It doesn't matter so much exactly what they look like now, just imagine how they work. Important to note, these things are also the spores. So this logic is implemented kind of as a function. Oops. Okay, here we go. Let's just say now you want to apply like this map function that you've implemented yourself that exists as a spore. And this f thing here, this f guy, is the user-provided function that you want to apply to all the elements in your list. So I don't know, let's just say, since it's a list of integers, this is +1 on everything. Okay? So this is the logic that you provided in your framework. This is the logic that the user gives you. Okay? And I'm just kind of like queuing this up for now. Like so basically you call apply on the silo ref, and you give this. Oops. And maybe you do another map, and you multiply everything by 2. Who cares? So you do map basically, use your logic that's implemented as map, and then now maybe you want to do a reduce. So you have your reduce spore thing. You have your function that you're going to pass to your reduce, and now you're actually going to want to get a value back, right? So this is when you call this send thing. So what the send thing does is it basically composes these functions. Well, beforehand, these functions are composed, and all of this stuff is composed and sent using send. That's then eager. Like right when that send thing is called, all of this stuff gets sent over the wire to the data that represents this, or the silo that represents this list of integers. Okay? So this is what it looks like the moment you hit the send button, basically. So you have this silo ref that was always pointing to some silo existing on another machine. Your send thing happens. So the runtime sort of receives the message, and it knows how to apply it to this piece of data. Like it knows where it is and how to apply it. And then these things get materialized. Like this little graph gets built. Does that make sense? Now is when is when this integer gets sent back and the future is completed with the integer. Is that clear? And that's the basic idea. So this program model, just like an akka framework, handles like the messaging and uses like netty and whatever underneath, and it does all that crap for you. But you're reasoning about things like you're applying functions to data. And another important point is you can actually get rid of these intermediate data structures by doing composing these functions and like not calling so many applies. Like this is the logic. This is really meant for people who want to build something that's distributed, right? And so you can do these optimizations yourself, like using like these lazy ideas. Like I'm just going to have something that just takes stuff and then uses apply only until you have some other method that uses the send, something like this. And yeah, like I said, these things can be trees. So you can make like graphs of computation from this. Like it's not just like here's one thing you transform and you get a new thing out. You can make these huge graphs of all kinds of different, that represent a bunch of transformations that you do to a piece of data. And that's cool because if anything ever like craps out and dies, you can always just apply all of those functions again to it, right? Like this is how Spark works. This is why Spark is so smart. So the idea is that you're actually building like a persistent data structure between machines. So you have pieces of data on one machine. You've got like the little, a cute little data structure that represents all the transformations that you end up applying to that data. And you're basically like making, you're replicating all of the logic that you wish to apply. And it's all serializable. So all your functions, everything that you're doing is serializable. So you can just write all of this stuff to disk, or you can send it to someone else if you ever just in case I die here have all the stuff that I have done. All you have to do is traverse this data structure, collect all the functions, and then send them over. Does that make sense? Is that clear? Like why this is, this is just, you just kind of can restart everything. You don't have to worry about some weird corrupted state that happened. You have just some persistent piece of data, and then you replay out everything on top of it.
So one question.
Sure.
If you have a sequence of for 10 operations. They're all really expensive, and the 10th one fails.
Yep.
When you rerun it, are you going to do the first line again?
Well, actually, I don't help you with that. This is just kind of like, you know, actors are like, hey, if it fails, we'll like notify you, but good luck, you know? I mean, I would like to, whoops.
There's a button on there. If you push it again, it's the little play button.
Wait, I pushed it.
No?
Wait, nope, no, it doesn't, it's not, it doesn't like it, sorry. Okay. I'm sorry, I totally got distracted.
So
What was I?
If you
Oh yeah, I don't do any of that. Like I mean, this is something. So the idea is that you would kind of put the code in the middle to manage these things based on whatever is important to you. So, you get it?
Yes, but can an actor actually tell whether it has been run? Sorry, an actor can.
Oh, like, okay, how far it's gotten?
Yes.
No, not necessarily. You can. So basically, right now we can notify you if something doesn't exist anymore, if it died or something. But we don't do right now. I mean, that's a good question, and it's something we should consider. But we haven't. Like, we're just trying to figure out how to restart things if they die. Yeah. So I basically said all of these things already. So cool. So this is all I really wanted to like cover with this function passing stuff, just to give you kind of like the basic idea of how it works. To reiterate, you have these pieces of data called silos that are actually a persistent data structure. And all the operations, actually, that you apply to them are all serializable. So you can kind of save stuff if you want to. And taken together, you can sort of, it makes it maybe a little bit easier to recover from something dying, maybe just by design. And so I wanted to show you some stuff on my laptop, but we couldn't get the thing working. There's like some Apple TV thing. So I will maybe go put this up after I like walk away or answer some questions. But there's actually, so like I said, we're working on a paper. This thing is implemented, it exists. It's right now, the current status of it is that we have, well, right now it's built on top of like Netty, and we also have it built on top of actors just to see as a proof of concept to do the networking. But it's built on top of Netty, basically, and that's really the only dependency. We have a cute little, I mean, we got some like little demo applications. Like there's one, it's called, we have this group by key example where I can actually, I could, no, I'm not going to show it because it's like.
Heather, if
yep.
you actually want to show stuff off your laptop, you just have to do it from boot.
Yeah, no, it's okay. It's like I should have maybe prepared it nicer. It's like just some code that's hard to look at. So I can explain it more simply, and you can look at it if you want online. Again, these APIs and all of this, and like sort of the semantics of this thing is changing. So like if you think that there's something stupid or ugly, you should let me know. There's also in this, if you go to this Google group thing, there's also like a design document that talks about the primitives and why they're necessary and how you can implement things like unions and joins and all of that using them. So there's more detail if you're like, this isn't enough. Just go to this Google group thing and you'll see the sort of like working document. We're working on a paper about it right now. And yeah, so I think that's most of it. This also depends on, the other dependencies, I'm sorry, they're the spores and the pickling. And these things are released and usable for these purposes right now. No type system stuff in the spores, because that stuff is, I don't want people like shooting themselves in the foot with it. So I keep that secret. If you really want it, ask me. And that's currently the status of any of these things. If you have any questions about this stuff, or like the function stuff, or the serialization stuff, or the spores stuff, or any other random, like, I hate this method and that thing, why is it that way? I mean, I could try to answer it, but probably don't know. But you can ask me any random Scala question if you want. I think that was all I was hoping to say tonight. So does anybody have any questions? Sure. What's up?
Can a data structure exceed the size of one machine without something that's like built into the?
No, not yet. That's important.
Heather, can you repeat the question?
Good, yeah.
Run around.
I'm the worst at that, yeah, okay.
It's okay, I'll remind you.
I'm so bad at that.
So what was the question?
So the question was, what happens if a piece of data gets to be too big for one machine? Or even better, what if you build some crazy graph that's too big and then, I don't do anything to help you yet because I'm just trying to make it work right now. But yes, good question. We need to do something about that.
Because that's something that then you, if you want to have one operation on all those things, is that then, I mean, that's kind of a lot of.
Well, that's the sort of the reason why you have these two ways to apply functionality. You have the lazy and the eager. So the idea is that you could at least try not to make too many copies of Wikipedia in memory on the machine that's distributed, like on another node. So that was like one reason for this, because you don't want too many intermediate data structures. So they're like views. If you know, are you familiar with views? Okay, they're buggy, good. But the idea is good. The idea is really nice. The idea is that basically you can get rid of intermediate data structures by kind of like lazily applying stuff and then only making the data structures that you need. So in the case where you do like map, reduce, you actually only make like one data structure that represents the result of the two maps together, and then you can like do a reduce on that. So you reduce the stuff that's in memory. So that's why things are designed that way. But we don't do anything explicitly to like manage memory. We're not like doing any sort of management of memory or any cluster or anything. We're just sending stuff to other machines and making sure it actually works.
Okay, thanks.
Yep.
So when you have
That's on?
yeah.
Hey, so when you have like the materialization of those views and you have the solid ref and send, it gets a future, but when that feature is complete, does that data actually like flow back to that?
Yeah, so you obviously don't want, like if your T is, a Wikipedia graph again, you want to, but at least you should see that future of Wikipedia, then you're like, maybe that's expensive. So yes, ideally like the sort of the nice pretty use case is like if you're going to do something like a reduce and you want just something small back, you want to keep everything that you've mapped on those machines, you don't want to move them.
What if you have data on two machines and you want to do something with them and get the result on the third machine?
Yeah, so the question is like, what if you have data on different machines and you want to do something with the results? So that's why this funny pump-to thing exists. So there in this repo, there's this group by key example. So the idea, like I can just illustrate the example really quick. It's very simple. Let's just say you have 4 machines and you have like hundreds of thousands of people on those machines and they all have an age. And let's just say you want machine A to have people under the age 25, then 25 to 50, whatever. You want to do like this. You want to like put them on their machines dependent on their age. Basically, there's there's this demo that shows how you can use these three primitives, this apply, send, and this pump to thing to do that, and a way that looks kind of like higher order functions on collections and stuff. So it's possible, but I didn't illustrate it. Yep.
The data processing example you gave really sounds a lot like the way Spark works today, in terms of map operations, not evaluated right away, and so on. Can you kind of highlight the differences between?
Well, Spark is a distributed system, and this is just like a cute little like coordination mechanism between machines. So if you wanted to have like some database or not a database, but like something that maybe acts as a database, or like you have 2 different machines with 2 different pieces of data on them some way, and you don't need like this, like heterogeneous kind of like, homogeneous like, distributed list thing, and you wanted to build something like of your own that somehow coordinates between 2 pieces of data, or you wanted to like make your own Spark or something. I use Spark as an example because everybody knows it, and this is like a generalization of kind of like the Spark kind of, or more Spark, but also kind of MapReduce like model in the form of like something that's at the granularity of like an actor framework. So that's the difference. It's this tiny little thing that does communication for you, and it also it makes communication more tight. That's very important. Yep.
There is something I didn't understand about capturing the environment and getting it back. For example, if you were to capture an atomic integer or something that then can mutate enemy, do you completely freeze it?
Okay, so that's a good question. So the question is basically, there's the notion of like shallow and kind of like deep immutability. So I make sure you don't capture anything that like where the reference can be like mutated and changed. So vars. You can't capture those, but if you have like something else that's implemented in terms of all kinds of mutable stuff, I can't prevent that thing from being mutable. I don't deeply, like statically check that everything inside of this thing is mutable. Actually, that's to be honest, it's actually not the best idea, because most data structures that you use that are effectively immutable as you see them, like the list in Scala, this thing is implemented in a mutable way. Everything is actually mutable. So if I actually did do that checking, you couldn't use anything, basically. But no, it doesn't do this deep checking where it figures out whether or not everything inside of it is immutable. I think that's too restrictive. But you can do it, actually. If you read the paper, we show how. There's like some way of defining something that exists as a property, and you can connect frameworks that do static checking, basically, which is how it works. But
How do unused silos get garbage collected?
good question. Good question. How do silos get garbage collected? They don't, because they're all pointing to different things, and you kind of want to keep them in memory because you're probably doing something with them for a while. That's like the idea. We're currently discussing, well, what if you want to do some streaming thing? What if you wanted to, I don't know, maybe on the machine that the silo exists on, get rid of the intermediate data structures if you only need one? We could do that. We could make that possible. Problem is then that the whole making restarting the computation on something that exists, that goes away all of a sudden. So then being able to recover from some, given all these random, this composition of functions that you have, plus your piece of data, you can't go from that to the result anymore. So that's currently a design discussion. And if you have ideas. Alexi, be loud.
So I want to build up on the previous question about the difference in Spark. Obviously, this is Databricks. What does Databricks want to see?
Nothing. This is a research project, and I was just doing this on the side and having design discussions with people about it. So this is not anything that they have any
so it's not like
interest in.
Spark 2.0?
No, not necessarily. No.
Hey, the silo refs, are they locations of data on a particular machine on a network?
Yeah, they basically just contain information, IP address and whatever port and all that. So I didn't show how to make a silo, but you have to it's just similar to actors, or at least in Scala.
Okay.
Yeah.
So like in Erlang, right, you have the ability to at least globally register a name. So you can say you always talk to a name, and then you're not bound to talking to an IP, right? Yeah. Because I'm thinking in the case of the silo is not available.
Yep. So we don't have any we don't do any sort of global. So we don't do any sort of global keeping track of all of the actors that currently exist. It's you create one on one machine, it points to one on another machine, and if you want to somehow share the knowledge of that actor ref existing, or I'm sorry, that silo ref existing, you can serialize it, send it somewhere else. But that's what we let you do, basically.
Okay, thanks.
Yeah. Does anybody want to know any other random thing? Do you have other random Scala, questions or anything else that you don't feel like asking? Tell me now. I can't answer all of them, by the way. Don't think I'm some sort of know-it-all.
I was just wondering, related to spores, what would happen if in your closer you took as an example, a database connection and you send it over the wire, what would happen then?
Wait, a database switch? Connection? Oh,
connection.
yeah, so...
Something that's not meant to be serializable or...
Yeah, so that's when you use the type system extension. But, I mean, just as it is right now, it's not going to stop you from doing that, but that's the whole point of this type system extension. And the idea is then you can also compose these closures that have rules and stuff. So for example, imagine the scenario. So people use akka. I've seen lots of hands. Do people use futures? Have you guys used them together? Have you ever had a problem? Okay. Yeah. I mean, so I can go into detail why there are problems. But basically, if you imagined, okay, well, hey, the reason why there are problems is because basically a future is like a closure. It captures something that changes over time. That's the reason why it's a problem. Doesn't really matter. You can say, wouldn't it be cool if we implemented futures in terms of these spore things? It would fix all kinds of people's problems, right? Actually, wait. What was the point I was going to make there? There was a point. I'm not. Wait. Oh yeah, okay, I remember now. That was back onto the question of the constraints. So if this happened, let's just say, okay, well we know akka exists, and like let's just say that, actually, does akka still ship futures anymore? Because I mean they're in the standard library, but like they were shipping their own library next to it for a while. I don't think they do anymore, but at one point they did. Let's just say they all existed in the same like distribution library package. Okay. You know that this type that you have in your library should never be captured, then you can always basically put in the type system where you're like defining what a future should be, that it should always exclude in the type system this other type that you know about in your like library in your world. So then you would then get a static error saying, okay, one of your users tried to capture an actor, basically, and then again these things can compose. So if you have forget about a future now. If you just have a function that captured something, or that didn't capture something, you can compose these two functions together, and the composition of the two functions, like you don't lose constraints, you can add constraints and stuff like this. Yay! Oh wait, no more. Okay.
One question. So there is a SIP.
Yep.
There was a SIP outstanding for spores. Why do they need an SIP?
That's a good question. So is this like, okay, so this sounds to me like a Scala process. Yes, I will. So it sounds like, so let me ask if this is the correct question, then I will repeat the question. So this sounds to me like a process, evolution of the language kind of question, like, community contributions, how this all works, like what does EPFL and types have to do with things and blah. Okay, so you wanted to know, there's a SIP, why does it need a SIP, blah, blah, blah. Well, the whole point is to, like let people see this, not for it to be like some random surprise. Let people, like argue about why it's a bad idea or a good idea. Show situations where it sucks or it can be better. People have actually contributed quite a lot of ideas that have made it nicer, and that's why it exists. It also exists because we don't know if it's a good idea yet. I mean, it seems to be that everyone has sort of settled on it being a good idea, which means it should be eventually shipped in some kind of distribution in some way. But this is, to enable sort of other people, other than just like 6 people, to make decisions, right? Or to weigh in on a decision being made. In terms of like process and how this all works, and like, oh, here's an improvement document. Okay, world review it. When will it be in? Like, there is no answer on any of that because, there are a lot of different things that can delay something being included. I mean, type safes like binary and source compatibility agreements, for example, or it can be just like we're not sure about the implementation, or we're not sure it's a good idea yet. So like there's no, in terms of time, there's no like, in 6 months this will be in and da 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 da. It's just a way to put stuff up, let people think about it. If they want it to keep it or if they want to throw it away, they can say something about it, and then we can weigh decisions on whether or not to include it in the later distribution that way.
But I mean, I'm wondering in terms of language. So for instance, akka does not require SIPs. Is it the library, or do you actually need language change or implementation? So
SIPs should be, currently the opinion about SIPs is that library, like anything that would be shipped in the distribution, whether it be a change to like the semantics of the language, to the syntax of the language, or to just a new library or a new module or something that everyone's gonna have to pull in all of a sudden, this all needs a SIP. Why akka doesn't get one? Well, right. I mean, they're like a separate project. We do ship an outdated version of the library with the standard distribution, but I'm not. I mean, that's just because we pull in like a dependency, which is akka. It's really they're still a separate project. They have their own sort of way of making decisions, and we try not to basically break their library, I guess. Yeah. Anybody else?
All right. Big round of applause for Heather.